Hello again, I'm Astrophysics Chris. So to speak, I'm actually Chris Williams, but this is the fourth part in my series of revision for my astrophysics exams being held in October 2010. I'm wearing the same clothes as I was wearing in episode 3, so you know that this is being filmed on the same day. You might be wondering what date exactly my exams have been held. Well, it's written on that white piece of paper over there, which you can't see, because if I boost the resolution on this, then my computer will crash and you then won't see this video. Right, so in this video I'm going to be talking about cosmic star formation history, but in previous videos I've talked about how dust can make faraway galaxies seem brighter than what they really are, the so-called K correction, and there have been a number of surveys which have both sub-millimeter and infrared, which have been analysed in faraway galaxies at various redshifts in search of where fresh star formation is occurring. I'm going to start off by telling you about some multi-wavelength surveys and some factors which they have considered. They have avoided bright foreground objects at optical, mid to far infrared and X-ray wavelengths. They have also avoided bright radio sources, also, low galactic neutral hydrogen column density for X-ray observations is a requirement, and also the cirrus clouds, which I mentioned in the third video, the fine wispy conglomerations of I don't know what the right word is, but you know what I mean, don't you? A small element of dust that looks like a cirrus cloud, like the cirrus cloud you get here on Earth, but a small wispy structure, and they're going to be avoiding them in such multi-wavelength series, but that's going to add noise to the observations. By noise, of course, we mean it's going to lead to anomalous results when you're looking for galaxies at a faraway redshift, and galaxies that have been too faint to observe previously, and also galaxies that might be young galaxies and experiencing star formation. Right. Some facilities consider loads of surveys at the same time, and they consider them in different tiers. And this brings on to something called Malmquist bias. You might actually read more about Malmquist bias. It's spelled M-A-L-M-Q-U-I-S-T bias, and you might read about it on Wikipedia. By combining series of different types of wavelength, whether it be X-ray, whether it be sub-millimeter or infrared, there's better coverage of the range of luminosities that you can observe. Bear in mind, of course, that you use sub-millimeter when you're looking for very cold objects, in the sense that they are extremely far away, and it's quite a bit of a hassle for us to detect their very faint stellar signature here from ground-based and space-based observatories. So it's only with the sub-millimeter and infrared to some extent that you can detect such bodies. Right. Cosmic star formation histories are derived from obscured star formation indicators, and obscuration-independent indicators show that just as much evolution as the rest frame luminosity density. There is evidence that the interstellar mass function is top-heavy in the centre of our galaxy. In the local universe, not far from the Milky Way, star-forming galaxies avoid rich galaxy clusters which are rich in heavy elements like beyond helium. The very young galaxies are only hydrogen and helium rich, but the younger ones contain heavy elements such as iron, for instance. There is increased evidence that at a redshift of 1, star-forming galaxies detected at 24 micrometers are more common in the environment where there is heavy elements like iron and that sort of thing. So essentially, the closer the redshift is to Earth, the younger the galaxy is. Of course, that's logical, because that adds in with the argument that the galaxy that we live in is composed of elements that were created many millions of years ago. This is not the first time that the elements that we are made of, not the first time these elements have existed before. No, they've been recycled. We've effectively come from a supernova that's happened in the past. The dust scattered from the supernova, it then formed to create our current solar system, and that's true for the galaxy in general, it seems. So this is a very young galaxy when you consider the history of the universe, and hence you would expect to see star formation in the regions not far from the Milky Way galaxy, and you might have galactic mergers at higher redshifts, also leading to star formation. Remember, because the galaxies don't merge, it's just the dust surrounding the galaxies which crash into each other, leading to star formation being triggered. There's only gravitation effects that bring galaxies together, of course, and of course there are hints that sub-millimeter galaxies are found in environments where there are heavy elements in this local area, local to the Milky Way. The natural generalization of the Butcher-Ulmer effect is that's an effect you can read about elsewhere, that is to measure the cosmic star formation history in different environments, and this is currently an ongoing area of scientific research. You might have heard my watch alarm beeping just then, because I'm currently waiting for my dinner to be ready while I record this video, but I hope you'll join me for part 4, where I will continue to talk about how galaxies form, and we'll then be discussing computer analysis like the N-body problem, and we then go on to ultraluminous infrared galaxies and what they evolve into, and there will come a point where I'll be talking about exoplanets, because my exams cover a wide range of astronomy related topics. So I hope you'll join me for more videos, and I hope that I'm educating you and sharing my enthusiasm. I hope I'm sharing my enthusiasm of astrophysics with you, and this will hopefully be useful for me on the to my exams, and it'll be entertaining for you too. Okay, thanks for joining me, and it's bye for now. Bye bye.